Okay, so let's continue this chapter 3, and now the result we are going to see together is what we called the Martingale representation theorem for the Brownian filtration. Okay, so let's switch the. Okay. I have finished with Girsanov. Okay, I'm here. So the idea is the following. So Martingale representation theorem. Okay, so what we know for the moment. So we have seen together that if theta belongs to L2 prog of omega time 0 capital T, we have seen together that in this case, the stochastic integral that I can define, okay, is a continuous and square integrable Martingale with respect to the Brownian filtration. And be careful, because what we are going to see and to say now, okay, will be related to the fact that we work with the filtration generated by the Brownian motion. Okay, so in fact, we are looking for a reciprocal for this. That is, if I am a continuous and square integrable Martingale with respect to the Brownian filtration, I am up to a constant, because I know that here I have a centered process, the expectation is 0, okay, but if I add a constant, it's then nothing to the fact that I have a Martingale, okay. So we are going to see that any continuous and square integrable Martingales with respect to the Brownian filtration have, in fact, this form up to a constant. So it's a really remarkable result, okay, that deal with the properties of the Brownian motion itself. So my aim in this result here is to look for a reciprocal. Okay. In the course, we have already seen some situation where we have a Martingale with respect to the Brownian filtration. So we know, for example, that the Brownian motion itself, okay, is a continuous and square integrable Martingale with respect to FTB. Okay. And in this situation, it's easy to see that I have this form because I can write BT as the integral between 0 and t of 1 time dBs. Okay, so the Brownian motion that is itself a Martingale, okay, may be written as a stochastic integral where the constant 1 here belongs to L2 prog without problem. Okay. We have also seen, for example, that the process bt square minus t is a continuous and square integrable Martingale with respect to the Brownian filtration. And we have proved together at the end of the chapter 1, it was using the Ito formula, okay, okay, for bt square, we obtain that bt square minus t can be written as 2 times the integral between 0 and t of bs dbs, okay, where the Brownian motion itself, okay, belongs to L2 prog without any problem. Another type of Martingales we have seen together is exponential theta bt minus theta square t over 2. That was a continuous and square integrable Martingale with respect to the Brownian filtration. And in this case, okay, if I want to obtain the integral representation, so in fact, it's a computation I have done in the framework concerning the Gersonov theorem, but let's do it another time, okay. I can use the Ito formula for this one, okay, so I can write it as exponential of xt with d of xt that is equal to theta dbt minus theta square dt over 2. And if I apply the Ito formula with the exponential here, I obtain what? I obtain that d of f of xt is equal to what? It's equal to f prime xt d of xt, the classical beginning of the formula, plus the extra term coming from the quadratic variations, that is f second of xt multiplied by what? So the term, the square of the term that is in front of dbt in the Ito representation of xt, that is here theta square dt. And I obtain what? I obtain here, okay, so f prime is equal to f second is equal to f, okay, so I obtain here simply exponential of xt, d of xt that is given by this Ito decomposition, plus 1/2 f second of xt that is here simply the exponential of xt, theta square dt. And I see that, as in the case of what I have done for Gersonov, this one and this one simplify, and I obtain simply at the end exponential xt theta dbt. Okay, I obtain this term here. Okay, and so I can write that my exponential theta bt minus theta square t over 2 can be written as what? So the value of this process at 0, that is 1, plus the integral between 0 and t of theta, okay, exponential theta bs minus theta square s over 2 dbs. And once again, I see that this martingale may be written as a constant, that is its initial value here, plus the stochastic integral, where I can prove basically that this one belongs to L2 prog. So if it's not clear for you that this one belongs to L2 prog, first it is progressively measurable because it is continuous and adapted. And to check that the integral, the expectation of the integral of the square is finite, okay, but you can compute it explicitly in this situation, okay, and prove that it is finite, okay. So in the 3 examples of martingales that are related to the Brownian motion we have seen at the beginning of the chapter 1, I see that I can write them as a constant that is in fact the initial value. So 0 for the 2 first case and 1 for the last one, plus a term that is a stochastic integral of an element in L2 prog. Okay, The idea is to do the proof of this result for any continuous and square integrable martingale with respect to the Brownian filtration. So it's what we are going to do now. Okay, and it's based off one result that is called the Ito representation theorem. Okay, that tell me that any random variable that is square integrable and measurable with respect to f capital TB. So here it's the Brownian filtration, because here, if you don't put the Brownian filtration but another filtration, of course, you don't have this result here. Okay, maybe written this way: f equal to its expectation plus a stochastic integral between 0 and capital T for theta belonging to L2 prog. Okay, and I say that if I have this result, the Ito representation theorem for square integrable random variable that are f capital TB measurable, then I have this result without any kind of problem that is called the Martingale representation theorem, that tell you that if I am a continuous and square integrable martingale with respect to the Brownian filtration, there exists a unique stochastic process theta belonging to L2 prog such that I have this. MT is equal to, in fact, its initial value, M0 here, plus what? Plus the integral between 0 and small t, theta of S dBs, where theta is an element in L2 prog. Okay, so first of all, I just want to show you that the first result implies the second one. Why? In fact, if I take f equal to m capital T, okay, so using the Ito representation theorem, this one may be written as the expectation of m capital T, I use this, plus the integral between 0 and capital T of theta of S dBs. I have this one, okay, this equality from the Ito representation theorem that I admit for the moment. Okay, and I want something for MT, but I know that M is a martingale, so MT is equal to the conditional expectation of M capital T given FTB, because, okay, MT is a martingale, okay? So I can use this, and I plug inside M capital T, so I obtain the expectation of M capital T plus the conditional expectation of the integral between 0 and capital T, theta of S dBs given FTB. But I know that the process related to theta of S dBs, okay, the integral between 0 and small t of theta of S dBs is a square integrable and continuous martingale. So in particular, this conditional expectation, because theta belongs to L2 prog, this conditional expectation is none other than the integral between 0 and t of theta of S dBs, from what we know concerning the stochastic integral on L2 prog. And so it's finished, because MT being a martingale, it is in particular constant in expectation. So this may be written as, in fact, M0. I have written expectation of M0 here, but I know that F0b is the trivial sigma algebra. So any random variable that are F0b measurable are constant. So in this case, expectation of M0 here is simply equal to the initial value. Okay. So basically, this result is a direct and easy consequence of this one. Okay? Direct and easy consequence of this one. Okay. But just a remark concerning this. So you will see that we are going to use this result in the case of the chapter 5, that is to prove that the Black-Scholes market is complete. And you will see that this notion of completeness for a financial market, okay, is related to the capacity to hedge, okay, European type product, let's say. So this result, from a theoretical point of view, will allow us to prove that this market is complete. And the strategies, the hedging strategies, okay, will be related to the existence of this process theta. Okay. So let just me say that in the proof we are going to do of this result, okay, theta is not known explicitly. Theta is not known explicitly, so it means that for financial applications, a priori, I have a theoretical result, but not a practical result, because if I need to find the theta concretely in order to build hedging strategy, this theta is not given by the theorem. The theorem just tell me that such a theta exists, okay? So as a parenthesis, okay, I can just say that for an explicit theta, C, but in fact, I do a course in the second semester that is called Maillard calculus and Monte Carlo methods, okay? See, by my course of the second semester. Okay, that is a course concerning what we call Maillard calculus. That will give you explicitly the theta. But it is out of the scope of this course, okay, this present course, okay? So whatever, I have this theoretical result, okay? And then I want, okay, to prove it now. And I have seen that in order to prove it, I just have to prove this one. Okay, so let's prove the first theorem that will conclude my today's session. Okay. So let's write it this way. I erase the other things. Okay, so proof of the theorem. Okay, we do the proof. Okay, so let's do the proof. First case, I will consider for F a very particular, I will consider for F a very particular case, okay, that is this one. So for capital F, I take the following. Exponential integral between 0 and capital T, h of s dbs minus 1/2 integral between 0 and capital T, h square of s ds. Why not? Okay. And after we are going to see that if I have the result for this one, I will have it for everybody. And I will explain why just after. Okay, so what I have here, so if you have in mind what I have done in the case of the Girsanov theorem, okay, we have seen together that, okay, it is something that is not very far from the LT in the Girsanov theorem, okay? So there is just a sign that is missing here, but whatever. Okay, if you change h into minus h, okay, you obtain exactly a particular case of LT in the Girsanov theorem. Okay, so I have this one, okay? So I can write it as my f is equal to the exponential of x capital T, where d of xt is given by ht dbt minus 1/2 h squares t dt. And of course, in order to give sense to this linear integral here, I need to take h belonging to L2 of 0 capital. So I have this one, and so I can apply, okay, I can apply the Girsanov, the Ito formula. The Ito formula will tell me that, okay, so by the Ito formula, so you apply the Ito formula for f, okay, of x is equal to the exponential, okay, and if you apply Ito to this case, you will obtain that f is equal to the value of this process when capital T is equal to 0, that is equal to 1, plus, in fact, the integral between 0 and capital T. Okay, so in fact, it's more or less the previous computation in the previous slide. Okay, I have done the computation for this case here. Not this one here. That was just the case of an h equal to a constant, but I can apply the same Ito formula here to obtain that you have here 1 plus the integral between 0 and capital T of h of u, okay, exponential integral between 0 and u h of s dbs minus 1/2 the integral between 0 and u h square of s ds dbu. Okay, it's the Ito formula that give me this. So for this, I obtain a theta here. Theta of u given by this expression. Okay, so the only thing it remains to check here is that, okay, my theta obtained this way by the Ito formula is in L2 prog. Okay, so first I see that here, okay, I have here something that is a Wiener integral, okay, a Wiener integral here. So here I have deterministic processes here and here, okay. So to check that I am in L2 prog, first I can say that I am progressively measurable because I know that this, okay, this stochastic process is continuous, is adapted. So this one is continuous and adapted. So I am progressively measurable. Theta of u is progressively measurable because it is continuous and adapted to the Brownian filtration. Okay. So I just need to check if theta is square integrable. So my question here is, this one belongs to L2 prog? I said that for prog, it's okay because continuous plus adapted, okay? And now it remains to check that the expectation of the integral of the square is finite. So I am interested in this one. Okay, so I have this. By Fubini theorem, this one can also be computed, okay, computed the integral of the expectation. So if I compute the integral of the expectation, here I have something that is deterministic, here I have something that is deterministic, so I can remove them. With a square, huh? And it remains what? It remains the expectation of exponential to integral between 0 and u of h of s dbs. Okay, I just plug inside theta square, that is the square of this one, so that's why I have the square of this one. Here I have a 2 that appear, that's why I have a 2 here, and here minus 1 over 2 multiplied by 2, that is minus, okay? And these one are deterministic, so I can remove them from the expectation. Okay, so let's continue the computation. this one. I erase the beginning. And my objective is to prove that what I have written in red here is just something that is finite, okay? But here, I have a Gaussian random variable because h is deterministic, so I have a Wiener integral here. So here you have a Gaussian random variable with mean 0 and a variance that is just equal to 4, okay, integral between 0 and u of h square of s ds, from the property of Wiener integral here, okay? So what I obtain that if I denote this one by star, that star is equal to what? But here it's something, so it's what I have inside here that is a Gaussian, and here it's something that is related to the moment generating function of a Gaussian once again. So I will obtain the integral between 0 and capital T, h square of u, okay, exponential minus the integral between 0 and u, h square of s ds, plus this term here that is equal to what? So it is something related to the moment generating function of a Gaussian, okay? The mean is 0. And I have, so sigma square, that is 4, integral between 0 and u, so u not a 4 here, h square of s ds, multiplied by 1, because here the t is equal to 1, and divided by 2 du. At the end, I can simplify a little these two exponential to obtain integral between 0 and capital T, h square of u, exponential, okay, of integral between 0 and u, because I have 2 minus 1, h square of s ds du. And this one is less than what? So here, okay, you have a process that is an increasing one. So I can say that I am less than the integral between 0 and capital T h square of s ds. This one is a process, if I mapping less than its value at capital T. So I say that I am less than the value at capital T, and I remove it from the integral. And the integral between 0 and capital T of h square of u du. And I know that this is finite because h belongs to L2 of 0 capital T. So what I have proved here is that for this one, it works. For this one, it works. Okay? Second case, step 2. I said that my result is okay for f of the form f equal to the sum of lambda I, okay, exponential integral between 0 and capital T h I of u dbu minus 1/2 integral between 0 and capital T h I of u square du. So why I have this step 2? It's very easy using, in fact, bilinearity. If I have it, I have the thing for this one from my previous step. For all of them, I have my representation, okay? And if I do linear combination, it will work because I know that expectation is linear and that the Ito integral is something that is linear. So bilinearity of the Ito integral. okay? So why I do this? But because, in fact, if I denote by star this kind of random variable as a step 3 that I will admit, or I will admit, but see lemma, okay, that is denoted by 3.2.1 in the lecture's note, to have a proof. Well, it's a proof that is not that long, okay, but you need to have some prerequisite in probability theory, okay, so have a look on it, and we can discuss about this one, okay, if you have some problem, but it's not something that it's fundamental because I will need this step 3 in order to conclude, okay, but the proof in itself, okay, is something that is dealing with measure theory, okay, and Laplace transform, so I don't want to enter into much details, okay, so you have the proof on the lecture's note, have a look on it if you are interested, but I can just say that in the step 3, I can say that the element of the form star, that is this one, the one that may be written as this kind of finite, so here it's finite linear combination, okay, so for any n, any lambda I, and any hi, you consider the set of the random variables that can be written as this kind of linear combination, and then the element of this form, in fact, we can prove that they are dense in L2 of omega f capital TB. Here I have f capital TB because it's the integrals between 0 and capital T here. Okay, so I am f capital TB measurable. Okay, so to conclude, we are going to use a density argument. So if f belongs to L2 of omega f capital TB P. Okay, but from step 3, what I have? There exists a sequence Fn of elements of the form star such that Fn converges toward F in L2 of omega F capital T B. Okay, using the previous density argument. But from my step 2, okay, these elements, the elements of the form star, okay, fulfilled the theorem. That is, okay, from my step 1, I have proved that I can write, okay, I can write something, excuse me, something of this form here. I can write it this way, where my theta here, that is in L2 prog. So from step 2, there exists a sequence of theta n in L2 prog of omega times 0 capital T with what? Fn that is equal to the expectation of Fn plus the integral between 0 and capital N theta n of S dbs. From step 2, I have this. And now, what I have to do, I have just to pass to the limit in some sense. So for the moment, be careful because I know that there exists a sequence, okay, and I don't know if this sequence is convergent or not. Okay, so before to pass to the limit here, okay, we are going to prove, in fact, theta of n is Cauchy and so convergent toward, let's say, a theta belonging to L2 prog. So Cauchy in L2 prog. So why it is Cauchy in L2 prog? It's Cauchy in L2 prog because, okay, I can write the following. I can write the expectation of the integral between 0 capital T of theta n of s when minus theta p of s square ds. I can write it which way, but I can use the Ito isometry. I know that this is equal to what? This is equal to the expectation of the square of the stochastic integral theta n s minus theta p s dbs with a square here. And this argument is the Ito isometry. So this one is equal to this one by the Ito isometry, but what is this one here? But I can use star, this one. And this is simply equal to the expectation of a square of what? Of Fn minus the expectation of Fn minus Fp minus the expectation of Fp here. And what I know that Fn converges toward F in L2. So Fn minus Fp, okay, or Fn is Cauchy in L2, but I know also that if I have the convergence in L2, expectation of Fn converges toward the expectation of F. So this one, okay, from this fact here, I have the convergence of this one towards 0 when n and p goes to plus infinity. So theta, okay, n is Cauchy in L2 prog, and so it is convergent. So if I come back to what I have Fn that is equal to the expectation of Fn plus the integral between 0 and capital T of what? Of theta n of s dbs. This one converges toward F, okay, in L2. This one converges toward the expectation of F because Fn converges toward F in L2. And what happened for this one? From the fact that theta n converges toward theta in L2 prog, by Ito isometry, I know that this one converges toward the integral between 0 and capital T of theta of s dbs convergence that is in L2. And at the end, by unicity of the limit, f is equal to the expectation of f plus the integral between 0 and capital T, theta of s dbs. Okay, so I have proved using my density argument that if f is in L2 of omega f capital T b of p, I have this one. The proof being done in several steps. First for, okay, this kind of exponential, where it is possible to do the job just using the Ito formula. Then, by linearity of the Ito integral, if I have it for it, I will have it for linear combination. I said that in the step 3 that these linear combinations are dense in L2 of omega f capital T b of p. And then I conclude using this density argument concerning, okay, this capital F. I use approximating sequences and I prove that I can pass to the limit in the representation. And to conclude here, just the last thing that I have to prove. Here I have proved the existence doing this. Just let's prove the unicity. Of this one. So suppose that you have this. And suppose that there exists another theta in L2 prog fulfilling the same thing. Theta S tilde dBs. Now what I have, this one, if I have this equality here, it implies that the integral between 0 and capital T of theta of S minus theta tilde S dBs, it's a random variable that is equal to 0. But if I take the expectation of the square of this stochastic integral here by the Ito isometry, so if I take, excuse me, it's not this one. So if I take the expectation of the square of this integral, so since this integral is 0, the expectation of the square is 0, but by the Ito isometry, what I have, that this quantity is simply the expectation of the integral of theta S tilde minus theta S square ds. So this is equal to 0, and so theta is equal to theta tilde in L2 prog. So you have here the unicity. While before, okay, I have the proof of the existence. Okay, so we have this Martingale representation theorem that is proved. So the only thing I have admitted is the fact that linear combination of such random variable is dense in L2. You have the proof of in the lectures now if you are interested in, okay? It is a mix between the use of Laplace transform, okay, and the monotone class theorem, okay? So I don't want to enter into too much details because this is not the main tools of my course, okay? But just understand that if I have this for this exponential, okay, by density argument, I will have it for everybody. And the key ingredient to do this, okay, is the use of the Ito isometry. Okay, so see you next week in order to start the financial chapter, okay? So in the chapter 4, it will be very general consideration on the way to model financial market in continuous time, okay? So I will do very general and basic remarks. And then in the chapter 5, we are going to enter into the details of the Black-Scholes model. Okay, so see you next week. Bye-bye.